But I get so bored with my nails so fast. They're the with the extensions. That you just like Jello. Yeah. Stop it. Remember where you like. Yeah. I'm gonna go with those guys because like whenever.
Everybody read chapter 3, chapter 5.
Yeah.
Good morning. I live down the street from her. Oh. Look at your hands. Look at all.
Everybody is able to see the quiz? Are you guys able to hear me? DJ?
Yes.
It's like solids and stuff like that.
Oh my God.
gas, don't put extra oxygen.
I still do it very good. So.
Guys ready? Yeah, I'll leave you guys 5 more minutes.
Yes. If you're multiplying everything. Oh, everything. But it's not everything.
Okay, I have an extra credit question. Okay.
The two of them.
So 57. No, I know, but that's not. Yeah. Or you change the numbers. But you put numbers in. Yeah, you change this one changes to. You love it.
Right. Yes, we did the next over 3 things times by 3. It'll cancel out.
Oh, so it's we can do it. Because if we see her saying, we just multiply. Yeah, I'm not gonna rewrite it.
Okay, everybody got their answers. Are you comfortable with your answers? Okay, so let me go ahead and put a spot for you on modules so you guys can upload it.
Okay,
What was that?
what is the extra credit?
It says, what type of footwear must be worn in the lab during lab?
Oh.
Yeah. Or-
Is it a CO for C for?
E is capital C, lowercase l. Okay, everybody's got it uploaded. You know the drill, take a picture, upload it onto Canvas. Okay. It's gonna help me out with, everybody got the pictures up?
Yeah.
Second. Sorry, I get anxious, you know, I'm so anxious today. It's a Monday. Aren't you guys excited?
No.
Sorry, my head's burning.
They took it off the kids one day and broke it. I was like, it was clean, it was SpongeBob. My kids were in the room, what's in the table. I just got out for a DD compound or something. I finished shattered. It was good. It is. I had it for a year. Before I tried. I didn't know. Where did we go over that? For 3. The last day.
Isn't it CNO?
Yeah, well, because this is a multi where everything's on. I gave them that molecule.
I think it's C.
I actually it's a compound. I know for sure the last one that's the elements. I'm sure. Or molecule. That was the first one, right? No. Well, for me. Yeah. No, A is so D is
For sure, because in our notes it says, you said NA instead of the which is the element.
Okay, so we have answers. Everybody's got answers. Everybody's got it uploaded. Yeah. Now remember, it has to be a JPEG, a PDF, a PNG, or GIF. Be uploaded. If it is an HEIC, then it's not going to be uploaded. If you have the motion picture, it won't be able to be uploaded. If you're having trouble, that's probably the reason why. Everybody got it uploaded? Okay, so let's talk. So, first one. Balance. Yeah, it is, right?
Already balanced.
Balance. Good job. Okay, second one. Balance.
No.
How do I start? Okay, let's write down your elements. We have C, an O, and an H. Okay, so how many carbon on the reactants? Who sets the reactants up?
6.
Okay, so I have 6 carbon. Okay, how many oxygens do I have on the reactant side?
3.
How many hydrogens do I have on the reactant side?
14.
Okay, on the product side. How? Good, I didn't have to say the words. How many oxygens?
3.
How many hydrogens?
2.
Okay, is it balanced?
No.
Carbons by carbons. Okay, so what do I need to do?
Make it to 6. Add a 3 on the product side.
Oh, wait, hold on. So we had 6 in front of CO2. We had multiple people talking, so. Can you hear them? DJ? DJ, can you hear me?
Yeah, I can hear you. What'd you say?
I said, did you hear them? Can you hear the class?
Yes.
Okay, good. So we have 6 So then that would give us 6 carbon. How many oxygens?
Put a 7 in front of hydrogen.
Slow down,
H2O.
slow down. But let's get the numbers first, right? So we have 6 carbon. And then how many oxygens total now?
13.
So we have 13.
13.
Okay, good. And you said put a what in front of the hydrogen?
7.
On which side?
On the product side?
On the product side. So in front of the water?
Yeah, H2O.
Okay. You guys agree with her?
Yes.
Okay, good. So then that gives us how many hydrogen?
14.
14. Oxygens. We got 19, because we got 12 here plus
Oh, yeah, 19, yeah.
19. Ooh, that's nasty. So what do I need to do?
Go to the reactant side.
What was that?
Go to the reactant side.
Go to the reactant side, and what am I gonna do in the reactant side? Don't be scared.
19/3.
19/3 in front of the ozone.
Oh, yes.
Okay, and we know that I can't cut you guys up in thirds, can I?
No.
So I can't do that to it either. So what do I do with that? Third order,
Multiply it all by 3.
multiply by 3. Everybody got that? Okay, so when I did that, my final answer is gonna be 3 times 6. Three times 7. By 8. Okay, simple, okay. Not too bad. Everybody got it? Everybody, that was an easy one, right? So we did that one last week, huh? Okay. Okay, what does the law of conservation of mass mean? Anybody want to take a guess? In your own words. You don't put your own words? No? But you look at your notes, right? Okay, that's good. So at least you're looking at your notes. You know where to look. That's a good start. So tell me in their words, and then I want you guys to translate. Basically, what you put in is what you get out, right? So if you're putting in 50 pounds of sodium and 75 pounds of chlorine, then altogether you should have 125 pounds total, right? So what you put in is what you get out. Okay, so simply put, now scientifically, what we'd say is that so mass that is mass is basically conserved, so the mass that you put in should be the mass that you get out. So that means that mass is neither created or destroyed, it's just changing forms, right? That's basically what it boils down to. Okay. Now, question number 3. Identify which is a molecule, an element, and or a compound. C, capital O. What is that, by the way? It's a compound. Is that it? What's that? Well, you gotta put everything. It said and or, right? And or means it can be multiple, right? So that's that reading that this question. And or means it can be multiple things, right? This or that, or it can be this and, right? Okay, anything else it can be? Capital C, capital O. Is it all by itself? Is C all by itself? Or C and O together? Oh, they're together. So then they could be a molecules. What is the definition of a molecule again? What was that?
2 or more elements bonded together.
Say it again.
2 or more elements bonded together.
Oh, I can hardly hear you.
I'm
You guys hear
sorry.
me? I can
I'm
hear.
so
Come on,
sorry.
say it louder. Say it loud and proud.
It's 2 or more elements bonded together.
2 or more elements bonded together. Is C an element and oxygen an element, and they're together? They're written together? So that qualifies, right? Good job. Okay. S6. We have molecule. Anything else? What was that? I heard somebody say it under their breath. Don't be shy. You said you suck.
Is it an element?
It's an element. What type of element is it? Not di. Di meaning 2, right? Poly. It's a polyatomic element. Okay. H2O.
Compound?
Compound. And a molecule. Sodium. Na.
Element.
Element. Wait, that was said loud and proud. Anything else? Nothing else. That's good. Capital C, lowercase o.
Element.
Element.
Everybody knows the difference between E and A, right? I was going to throw something at you if you didn't know the difference. Like, look on the periodic table, right? Okay, so we want to make sure that when we're writing our elements, we're writing them the right way. Otherwise, if you write them both capitals, what happens? What do I think?
They're 2 separate elements, or they're 2 separate.
I think they're 2 separate elements that are brought together by bonding, right? And then I mark you wrong, right? Okay, not too hard, right? Simple? Good. Okay, let's get started. Today, we got a lot to cover. Okay, so we've talked about physical change, right? Physical change, we talked about chemical change. So you guys are familiar with physical change and chemical change? Are you sure? Are you feel confident? It's a Monday, you know, we're brushing out those cobwebs. You know, you guys had that weekend. It was that what? Thursday, Friday, Saturday, Sunday. Y'all got a little too comfortable, huh? Then I had to come back and say, nope, don't be comfortable. Right? Okay, so physical change versus chemical change. Now, can anybody give me a very general definition of physical change? Anyone? Hard to hear. What was that? Water into steam. That is a beautiful example. Yes, water into steam is a beautiful example. Okay, so if we go from water to steam, that is a physical change. Why is it a physical change? Why is it a chemical change? Because we're not changing the chemical identity. What does that mean? Still water. At the end of the day, it's still water, right? It's still H2O. We're not changing it to H2O. Okay? So, chemical change means what? Based upon that definition. what's happening in the case of the chemical change? We're changing the chemical composition or the chemical identity, right? Okay, so I gave you the example of beef burning sugar, right? Where we went from sucrose. You guys remember the chemical formula for sucrose? To basically carbon and water. Right? Okay, so let's see what you guys can do. Help me out here. Okay, so yeah, the first case, you guys, it's probably hard to see, it's a little light from here. So a log burning. Log burning. Is that a chemical change or is that a physical change?
Physical?
Those who say physical, raise your hand. Those who say chemical, raise your hand. Now think about it, right? Think about it. I want you to think about it before you raise your hand anyway. Okay, go back. That's the question. At the end of the day, can you get that log back?
No.
Oh, if you can't get it back, how is that a physical change? Because in the case of steam boiling, if I collected all that steam, I can make it back into water. I can make it back into ice cubes, right? So, but I can get that water back. But in the case of a log burning, can I get it back?
No.
So that would suggest if I can't get it back, what would that suggest to me?
Chemical.
That is a chemical change. That's right. Okay, so first one. A, chemical change or physical change?
Chemical.
Those who say chemical, raise your hand. Those who say physical, raise your hand. Those who don't want to vote, raise your hand. No, this is democracy. You gotta vote. What's that? You say chemical. Okay, good. Okay. B, ice cube. By the way, it's a chemical change, right? B, ice cube melting.
Physical.
Physical. Everybody agree? Anybody disagree? It's okay to disagree. You can't always go with the flow, right? But you are correct. It is a physical change. Okay, the last one. Glow sticks. After you pop them and they're going, right? Physical change or chemical change?
Chemical.
Chemical? For sure.
Because you're breaking the substance. You're breaking the substance to
And it can go back.
collect it. Never mind.
There you go. Actually, that's why you can't go back, right? After it glows, it's done, right? So you can't sit there and get it all bright again, huh? Right? Hey, good job.
So basically you just ask yourself, can it go back to its normal state, right?
Right. For right now, don't worry about it. We'll throw you out the window in a minute and you'll be like, hey, you have to change the rules on it, right? That's the best part about chemistry because we start making those slight modifications, right? To get you guys a little more well-defined. Are we good? Perfect. Okay, so now we have pure substances and a mixture. You guys know what mixtures. I don't need to talk to you guys about that. What are the different types of mixtures that we could have?
Scared to answer.
Don't be scared. That's an example. Sugar and water is an example, right? So is that a homogeneous mixture or is that a heterogeneous mixture? Yeah, it's also
Hetero.
it's a homogeneous it's totally dissolved. It's a heterogeneous if it's not, right? Okay, so depending on the state that we have it in, okay? So we already know what mixtures are. Mixtures are just basically two or more pure substances, right? That definition of pure substance, what does that mean? Pure, it's pure. Can I have pure cocaine? Can I have pure sugar?
It's the real deal.
It's the real deal. What was that? If it's pure, it means what?
It's pure, it's good.
It's 100%, nothing else is in it, right? So it's
Yeah.
not a mixture. If it's pure, is it a mixture?
No.
No, it's not a mixture. If it's pure, right? So pure sugar, right? Pure cane sugar from what? You expect what to be in there?
Pure sugar.
Sugar, right? Okay. If it's pure cane, you expect what to be in it?
Only cocaine.
Only cocaine. So we know if it's pure, it's not cut with anything, right? If it's cut with something, then that means it's a mixture.
It's a mixture.
Okay. So you can tell the street pharmacist, I know the difference between something that's pure and something that's a mixture, right? Okay.
Pull up to the pharmacy, like, I know the difference.
I know the
between
difference,
cocaine."
yeah, that's Okay, so let's talk about these solutions and how solutions can be effective, right? So how many of you guys make pasta? Anybody make pasta? Nobody not make pasta? Everybody here's made pasta at least once in their life. Right, good. That's good. So mama or grandma or dad or whoever taught you to make pasta. They always added salt, right? They added salt to that water. Why do they add salt?
They say to make the water boil faster.
To give us the only thing to give the noodles taste, because that's the only substance that can give raw
Doesn't it
taste.
absorb into the noodle?
So.
Okay, so we got it. So we said absorbance of noodles. That's what everybody says, right?
Yeah.
Flavor, right? You want to know the truth? Right? The truth is it changes the properties of water. We're like, it's a mixture, right? It changes the property of water. That means water will boil higher, right? Your noodles will cook faster. As somebody says, faster cooking, your water boils faster. In other words, you're raising the temperature so it'll be a higher temperature where water boils at. Right? So then that means your noodles are completely cooked without them getting soggy. You guys like soggy noodles? Anybody like soggy noodles? I hate soggy noodles, right? So you don't want your noodles to be soggy, right? And so by you using salt, it helps you sit there cook your noodles faster so they don't get soggy. Right? Otherwise, they start to get a little soggy. Nobody likes a soggy noodle. And then, of course, we like salt, right? So we like the flavor of salt too. So it does help the flavor. I'm not gonna say it doesn't, but that wasn't the original reason. It's changed the boiling point.
I've been lied to.
So that means that there are characteristics about these guys interacting, right? Because we know that salt and water, although it's dissolved in water, it's a mixture, right? And since it's a mixture, they're interacting with each other. And how they're interacting is kind of interesting. They interact by what we call intermolecular forces. Let me write that on the board here. Let me write it, I guess, write it on the board here. Get five markers. Okay, intermolecular forces. You guys know the interstate? The interstate. Why is it called the interstate? It runs between states, right? So I-5 is an interstate, right? It goes from California, actually goes down a little further, right? So I think it goes to Mexico. Yeah. I-5, and then it goes up to Oregon, Washington, and then to Canada, right? Is it going to Nevada? Okay, so we know that it goes up and down, right? And we know that it goes all the way up to Washington at least, right? So that's 3 different states it goes through. Inter. So intermolecular means that it's between molecules. So it's between sodium chloride and water, right? Intermolecular. So we have interactions between sodium chloride and water. So let me tell you about some of these forces. Okay, so that you guys will know in advance. I'll talk about them briefly. We have ionic, dipole. Okay, ionic basically means that it forms an ion. Let me tell you what an ion is. What the hell is an ion? An ion is something that is charged, meaning that it's plus or minus. You guys know what plus and minus is, right? So plus and minus. Okay, so an ion dipole means that you have something that's charged and something that's being influenced by that charge. So if something is plus, if you guys have a girlfriend that's really positive, go lucky, she gets up in the morning, oh honey, I love you, I love you, I love you, right? And she's just so happy go lucky. Oh, today is such a beautiful day. And you're not really a morning person, right? You're like, why are you so happy in the morning, right? Right? She influences you, right? And then you finally you get a cup of coffee and you're happy, right? Because she's happy, she kind of gets you going, right? So that's kind of what happens in the case of a positive ion influence a dipole. It causes them to interact. You know, first kind of initially you're like, we gotta get up, you know, and then eventually you kind of settle down a little bit, right? You know, but it's that first initial part, that's that dipole that changes, right? Because eventually you settle out, you level off, right? Okay, or you have that negative girl who don't like to get up in the morning, you know, she has to get up in the morning. It's gonna be a horrible day. And then that kind of sets your mood, right? Because then you're thinking, God damn, it's gonna be a horrible day. And then you're like, okay, wait, let me calm down a little bit, you know? And then you have to be the one that's positive and go happy, go like, you take a coffee and you'll be okay, right? Okay, so that's an example of an ion dipole. Okay, so those means that two different things are interacting, two different molecules are interacting in the same way. Okay, we have a dipole. Dipole. Okay, so kind of like, again, in this case, best way of saying dipole. Di meaning two, pole, right? Two poles, right? So we often will call somebody bipolar. What does bipolar mean to this?
Two-faced, crazy. Two-faced, right? I don't know.
High and really low, right? And that's super crazy. Come on now. Let's be a little bit tolerant here. I have bipolar moments, you know. Some days I'm really happy when I see that everybody's passing the class. And then other days I'm really pissed when I see that people are failing for no reason. Like, why are you failing, right? So I go bipolar, so or bipolar on you, right? So bipolar basically means you have highs and you have lows, right? Some days you're really high, some days you're really low. Sometimes it's not even days, it's moments, right? It could be a moments in a day with somebody who's severely bipolar, right? So they'll get really high, low. And this is kind of funny because we talk about the same thing in chemistry. Dipole basically means positive and negative, high and low, right? Because we think of positive as being a high, right? And we think of negatives as being a low. Okay, so in the case you have two molecules that are swinging from high, low, positive and negative, right? So they interact with each other because when one is positive, negative, when the other one is positive, so they're interacting that way. Because we know that, you guys know that opposites attract, right? Everybody learned that in high school, right?
Yes.
We're always making the bad girl or making the, you know, because they're opposite. Change him, right? Right? So we all learned that real quick in high school, right? Opposites attract. Chemistry, we're taking it to the extreme. We're really saying that opposites are going to be attracted, right? And so if you're high, you're positive one moment, and then I'm low, right, negative, then we're going to attract each other, right? Because you're going to try to be happy go lucky, and I'm going to be life sucks, right? And we just naturally attract that way, right? You try to cheer me up. Oh, let me cheer you up. Let me make you okay. And then as soon as you get low, then I get high. Oh, I got that cake. I'm feeling really good. And you're like, this cake is sucks. It was not the best cake ever, right? And so you just kind of play off of each other, right? So that's the dipole line. Okay. Hydrogen bonding. Hydrogen bonding. I like to think of hydrogen bonding as kind of like a fist bump, right? But it's kind of like a special fist bump that requires hydrogen to be present, right? And there are things that hydrogen has to be next to certain elements, right? If hydrogen is next to oxygen in terms of its bonding, then it's going to form a hydrogen bond. If hydrogen is next to nitrogen, it's going to form a hydrogen bond. Okay, so let me give you an example. So if we have H2O. So in other words, we have oxygen next to hydrogen. Okay, so this line here just represents a bond. The line here represents a bond. Okay, or if we have hydrogen next to nitrogen. Okay, again, these represent bonds. So in this case, they're going to form a hydrogen bond when they interact with another molecule, right? So if these guys interact with each other, the hydrogen is going to interact with the oxygen, and this hydrogen is going to interact with that nitrogen, right? Because this guy, they form what we call dipoles, right? Again, that dipole. This guy is going to be what we call partially negative. I'm going to draw partially with this symbol. That there is delta. It's a Greek letter meaning change. This guy's going to be partially positive. The hydrogen is, and the nitrogen is going to be what we call partially negative. Okay. Now, because positives and negatives attract each other, then in this case, this hydrogen on the water is going to be attracted to that negative. So this partial positive is going to be attracted to that partial negative.
Will the middle one always be negative?
Well, it depends. And we'll talk more about that. It kind of depends on where they're located in the periodic table. Now, I'm going to tell you this now because we're going to be talking about it later. Everybody has a periodic table will be able to extra. Okay. Anybody not have a periodic table? Okay, that periodic table. Good. Okay, so at the very end, at the top, we have what we call groups. So the numbers at the top represents groups. The numbers here. This represents groups. Groups. Let me pull up the periodic table. You guys don't like yourselves? Why you guys are so self-conscious? This is what we see, right? It's okay. You guys are such beautiful people. Embrace your beauty. Okay, so at the very top up here, those are periods. Those are groups. At the top are groups. And then on the sides here, these are periods. Okay. So groups and periods. If you guys look at group 18, group 18 is the noble gases. Noble gases are kind of like that term noble. What's noble mean? Royal, right? It means like royal. You think about Queen Elizabeth, all of that stuff, right? And so when we think about royal, do we think that we're like the royals? No, but we want to get like the royals, right? You want to marry a prince, right? Or marry a king or something like that, or acquire so much wealth that you're like a prince or a king or something like that, right? That's our goal, right? That's the reason why we're all in this class, because we want to get to that next level. We want stability, right? So the noble gas kind of represent stability. In chemistry, they represent stability. Everybody wants to be like the noble gases. Okay. At the end of the day, you want to be like the noble gases because they're like, they got it all. They have it made, right? They don't have anything to worry about. Everything is perfect for them. Okay. So you want to try to find ways of getting that. And the closer that you are to being a noble gas, you're going to do certain things to sit there and try to get that way, right? So if we look at group 17, these guys are called halogens. Halogens, you kind of see the name up here in the corner. That's halogens, right? You guys see that? So halogens, they're like one away from what, right? So a lot of this is based upon what we call electrons. They're electronic, okay? So they need one more electron to be like a noble gas. They need one more electron to be stable. That's kind of like you have $1 million in your bank account right now, and you're like, okay, if I get $1,000,001, I consider myself stable, right? Shit, if I have $100 then I consider myself to be stable, right? So if I get that one, I become stable, okay? So that's kind of like them. They're like one away from being stable. So they're going to do pretty much anything to get there. So if I see this $1 on the field, I see the stone that's sitting out here, I'm like, stick it in my pocket, go sell it at the Walmart or whatever, you know, for that $1 to put in my bank account so that I get stable, right? Okay, so they're going to be anxious to get stable. They're going to do anything to try to get stable. So they're going to be willing to take electrons from other people or other elements to get stable. They're going to be anxious about it. Now they're share, right? They'll think about sharing electrons, right? But right now they're like, any way that I can get there, I'm going to get there. So if I have to share with you, then I'll share with you. But if I could take it from you, then you're asking to bully you for that electron, right? That's my electron. Okay, they're one away. Okay, oxygen. It's here. Oxygen is two away, right? So it's not as strong as the halogens. It's not thuggish like the halogens, right? It's a little more, okay, diplomatic, you know. Hey, but if it gets the opportunity to take from you, right, it'll punk you, right? It'll smartly punk you, but it'll still punk you for those electrons, right? Not as violently as those halogens will, but it's going to try to get that. But it needs to get two of them. And then the further you get away, it takes a little more effort. Now, carbon is what I call a whore. That's right, I said a whore. Okay, now you're going to say why carbon is a whore. Well, carbon's a whore because carbon likes to do it like this. It's like, what is it that you need? Let me take care of you, right? Do you need electrons? I can hook you up with electrons. Oh, you want to give away those electrons? Give them to me, right? Carbon can go both ways. It can take or it can give, right? It likes to be in the middle, right? And that's part of the reason why carbon is the center of life, because it can go both ways. It can be taken and given, right? And it has the ability to form what we call 4 bonds easily. And it's happily to do it. It's like, ooh, let's bond, right? It's an opportunity. Okay? Okay. So, and we'll get more into this, and you guys will start clicking right now. So this is just kind of an intro to kind of the chemicals, right? But you want to know it's all about stability. It's all about energy. Okay? Energy plays a huge part. The goal is to try not to use energy, because if you're rich, do you use a lot of energy? Do you do your cleaning? Do you do your cooking? No, you don't, right? You have somebody else do that shit for you, right? You're like, sit on my ass. You know, I'm gonna go shopping, girl. You know, it's like I need to get my hair did and stuff like that. That's no energy on you, right? It's energy on everybody else. So it's about using the least amount of energy as possible. So you're trying to find ways so you don't have to use a lot of energy. It's about low energy. So energy has to be conserved, right? Because you got to think about it when you don't got a lot of money. You got to think about how to use your energy. You can't do everything, can you? I try, man. I try to take care of my girlfriend's son. I try to, do all of my grading. I try to do this. Shit, by the end of the day, I'm like, school coming out because I'm so damn tired, right? Because I'm exuding so much energy, right? I need to find ways to be a little more efficient, right? I need to conserve that energy, right? So I need TAs to sit there and help me do all of the lab prep, and then help me with, okay, you guys look at those damn, lab reports before they come in, so I can make sure I just check them off, right? Make my life easier, right? So you guys make sure you go see those TAs before you start stuff in, right? Hint, hint. Okay. So the thing is that it's about conserving energy. At the end of the day, it's all about energy. Okay, and we're going to be talking a lot about energy. We're starting today, and we're going to continue talking about energy. Okay. Are you guys with me so far? So we were talking about those intermolecular forces. Now that is a form of energy. Again, you want to interact with things that are going to make your life easier, right? Make things lower in energy. You don't want to interact with, how many guys date crackheads? Anybody date crackheads? So anybody ever dated a crackhead? I'll tell you, I have.
She raised her hand.
I'm not gonna lie to you. I've done it. To be honest, right? That is a lot of fucking energy, right? You know, yeah, I am not kidding. You pull them out of crack houses and everything, you chase them down and try to keep them from doing stupid stuff to themselves. It is a whole lot of energy. It isn't worth it, right? It isn't worth it. You're like, Jesus Christ, what did I get myself into? And then when they start coming down, right? They get mean and nasty and they want to throw stuff at you and cut you and stuff like that. Wait a minute, hold on. I just saved you from a crack house. Think about what I just did, right? Come on.
They're carbon.
I'm just kidding. Exactly. They're definitely not carbon because carbon's like, cool, collective, they're beyond, you know.
But it goes on. It could be cool and collective. Like, hey.
They're more like the halogens, hot mess. I swear. But anyway, it's about energy, right? At the end of the day, you realize after you date a crackhead for about a year, you're like, okay, I'm good on that. I've learned my lesson, right? There's no change in the crackhead. They're gonna be who they're gonna be. That you're off, right? And you're like, that's enough. I'm done. Okay. So you learn real quick that takes way too much energy, right? And you want to get to find that nice girl or nice guy, or like, oh, yeah. Okay, man, I don't have to chase her down and hunt him down in the drug house or anything like that. We're about getting shot on the daily, it's good, it's like, it's good, and so you appreciate those things, right? Again, you go from that state of high energy to low energy, right? That's what it boils down to. That's what life is about, right? That's what chemistry is about. It's all about the same thing, okay? I'm sure you guys have never had a class like mine before, right?
No, it's real, it's cool.
Yeah, right, yes. Energy, it's about that energy, right? You think about it, you'll think about it. You see those movies where the crackheads are, and then when they come down, you're like, geez, Okay. So pure substances, we talked about them, right? If it's pure, is it a mixture? Can it be homogeneous? Maybe, because homogeneous suggests that it's a mixture, right? So if it's pure, it can't be homogeneous, right? It's pure, right? It's pure. Even though it's uniform, but it's all the same thing, right? So it's not a mixture. Homogeneous suggests that we're talking about mixture. You got to be careful, right? Because they're really quick to trick you on the exams, right? Not my exams. Not my exams, No, that is something that I do put on my exams, right? Because you need to be able to distinguish, right? Okay, so we know if it's pure, it is not considered a mixture, right? So it's not going to be homogeneous, it's not heterogeneous, right? So, example of pure bromine. Okay, DJ, we love your conversation, right? Thank you. Okay, no, we've all done it. Come on now. I know I've done it. I'd be cussing and talking shit about my administrator and leaving it on mute, and my administrators listen to me. I'm like, oh shit. I mean, I have a job tomorrow, so yeah. So we've all done it once before. So we have pure bromine, we have pure water. Now, if we mix them together, right, we have a mixture. So is that mixture homogeneous, based upon what you guys see there, or is it heterogeneous? What do you see, right? It's about what you see. It's all uniform. It's a light brown color, right? Beautiful light brown color, but it looks all the same. But in reality, we know that we have water and we have bromine, water, right? You guys will be able to sit there and distinguish based upon those little balls and everything, right? You guys are familiar with the stick figures, right?
Yeah.
Right? So pure, right? Mixture. You guys can see that, right? Okay, so we know that this is a mixture, and we know that this is a homogeneous mixture because it looks uniform, but we know that there are two different substances that are in there. Okay? And then here, if we add more bromine, it just gets darker. Is it homogeneous or heterogeneous? Is it hetero? Does it look the same throughout the entire thing? It's homogeneous, right? It's still homogeneous. It's just darker, right? So you can't distinguish between it. If you can distinguish between it, like you see one that's bright red and one that's like green or something like that in that solution, then you would say it's hetero, right? Okay, hetero meaning different, okay? So we've talked about homogeneous, we talked about heterogeneous, okay? Okay, now, if we have water, we have ethanol. Ethanol is drinking alcohol, so basically vodka, right? So if I have water and vodka added together, homogeneous or heterogeneous? Homogeneous. It looks all the same, right? You can't tell the difference. When you take that shot, you can, but you can't tell then, right? Okay. So now the thing is that if we're good at what we do, right, as chemists, we can separate things based upon their physical properties. Okay? So for instance, if we separate a mixture of iron and sulfur, so I can take a magnet. A magnet is going to collect the iron and it's just going to leave the sulfur. Okay? So I use the physical properties. We know that iron binds to magnets, right? They're attracted to magnets. Right? So I use the fact that iron is attracted to magnet to sit there and separate it from that iron and sulfur mixture. So I can collect all of the iron and just leave all that sulfur. Okay. Now, if I wanted to, I could do the same thing with ethanol and water, right? How many of you guys watched the Ducky Brothers and distillation and whiskey making and all that stuff? Anybody watch that on YouTube? Okay. That process of making whiskey, right? Anybody know the process of making whiskey? Well, you ferment it and everything like that. After you ferment it, what do? You distill it, right? So distillation, right? What is distillation? What's that process?
Boiling to separate.
We're boiling to separate the chemicals. So what are we separating? We're separating the ethanol from water. He said he didn't watch it. He knows he's been watching it. He's been brewing since he was 2, right? Okay, so anyway, he uses the fact that ethanol, it actually boils at like 86.7 degrees Celsius, where water boils at 100 degrees Celsius, right? So if I get the temperature stabilized and it's slightly above 86, but below 100, then guess what I'm getting? I'm getting ethanol, right? I'm going to get ethanol. So I'm going to be able to separate anything that is able to boil below that 86 degrees, that 86.7 degrees, right? Anything that I'll be collecting off, right? Okay. So, but mostly the ethanol. Okay. Long as it's below that 100 degrees, right? Which is where water boils. Okay. So we know water boils and turns into a gas and all that stuff at 100 degrees Celsius. So I'm going to write that. Okay, so again, distillation. Good job. So distillation allows us to separate things based upon physical properties. One of those physical properties is boiling point. Boiling point is a physical property, right? So we know that ice melts at. Where's the ice melts?
32.
I'm just kidding. Actually, no, don't just kid me. It is actually 32. 32 degrees Fahrenheit. Don't just kid me. So it's 32 degrees Fahrenheit, which is actually 0 degrees Celsius, right? So 0 degrees Celsius, ice freezes. It's also the point where it melts. If you get slightly above 0 degrees Celsius, right? You need a little bit more, you need a kick to get it over the edge, but it'll actually start to melt, right? So 0 degrees Celsius or 32 degrees Fahrenheit. Okay, water boils at 100 degrees Celsius and 212 degrees Fahrenheit. We'll talk more about that here in this next chapter. Okay, so distillation is one way of separating. How many of you guys make coffee? Anybody make coffee? Do you guys make coffee the old way, or do you guys use a Keurig?
I use a Keurig.
The old way? Keurig. I'm like Korean too. But the old way, back in the day, we used to make pots of coffee, right? I know it's hard to believe. We did make pots of coffee back in the old days. And we used those things called filters. Guess what those filters did? Okay, so they allowed the solids to stay stuck in the filter, right? And we just got that liquid, right? So that's another way of separating mixtures, right? So if something that's a solid and the other thing is a liquid, guess what I can do? I can use a filter to sit there and separate. Guess what? You guys have been doing this for years, right? We've been bootlegging, we've been making coffee. So we've been playing with chemistry our whole lives, right? How many of you guys drink distilled water? Or purified water, or bottled water, right?
Yes, purified water, we think, yeah.
Yeah. So I'll show you guys some studies on purified water here. Soon. In that case, we often will use reverse osmosis to sit there and get that water purified, right? So we're not getting all of the other things added onto it. Right? And so we use forms of filtration as well, because we put a nice little filter barrier. And then we play with the osmotic pressure to sit there and cause the water to flow through and just collect the water. We'll talk more about that. Okay, so this is an example of an old distillation, right? Or what we would use in chemistry. Okay, so here we boil the water or boil whatever fluid we're working with. And then it would form vapors. Here it would get cooled down. And then we collect that pure liquid, right? In this case, it would be water. We're working with alcohol. We set up the temperature so that we would just boil out the alcohol and we would collect the alcohol. Okay. That's what my organic chemistry is doing. It's summer for this last semester. And if you take my full series, you get a chance to make wine, and you get to make hard liquor, and
I get to drink it, Cliff?
no, you don't get to drink. This is a college campus. I get to no. By the end of the day, you're a little tipsy. No, the thing is that you do make it, and the philosophy is that if you're of age, if you're 21 years old, you made it, right? I let you guys take it home at the end. Although I keep a couple of bottles, because eventually we're going to try to get them marketed out to our contributors, to the program. So.
I'll be like, I come to class.
Yeah, I'm actually in the process of writing for our curriculum. We want to do a community program where we're actually going to do the chemistry of alcohol. And so it's just going to be a summer program where you learn how to make various forms of alcohol. So, but you have to be of age to take a class. So,
Okay.
Yeah. So just so you know, and it's going to be a summer thing. It's going to be community. So it'll be the first time that we're offering probably next summer. So I'll have this class in the morning and then that class in the evening. So then I can go home a little tipsy. So anyway, gravitational filtration. So that's just basically what we do in our coffee filter, right? So the coffee basically flows through with the water. We separate the fluid, the solution, and we keep the solids in the filter. Okay. Elements. So we've talked about elements, we've talked about compounds. You guys are already, and we're like really ahead of the game here or something, right? You guys know the difference between an element and a compound? Okay, I would hope so. Okay, so we know that a compound, if we mess with it chemically, we can break those down into elements or smaller compounds, right? You guys already know that by chemical reactions, right? So this is just basically showing it. So if we have a mixture, the thing about mixtures is that they're interacting by intermolecular forces, right? Intermolecular, right? And then so we can separate them by their physical features, right? Water, alcohol, we can separate those, right? And so we can end up with pure compounds in those cases, or pure elements. Now, chemical compounds, a chemical which is pure, we can only separate it by chemical means into elements and smaller compounds. Does that make sense? Don't fall asleep on me. Okay, so these are some of the common elements that you guys come across and compounds, right? You guys, your lead in the pencil, graphite. Graphite pencils, really, right? Carbon. Copper pin, it isn't pure. Well, it's pure, but it's your steel boats, your lead weights, silicone, your copper wire, your silver bracelets, right? Anybody got pure silver bracelets? All right. So these are some examples of compounds that we use commonly, right? So we have Li, which is sodium hydroxide. We have developer, which is, I can't remember off the top of my head, it's copper something. We have rolades, or antacids. Anybody use antacids? Yeah. Oh, yeah. Okay, we have baking soda, right? Everybody use baking soda. We use it for everything, right? Keep our refrigerator from stinking, right? Cooking. Okay, we use it for, in the case if you spill acid, we use that in here for that. Chalk. So these are all examples of chemicals that we've come across and we'll come across. You guys already know how to write chemical symbols. We already talked about it. 2-letter or the single letter, right? You know the distinction. We've already talked about chemical formulas, right? H2O. We know what an atom is. We know what a molecule is. Right? Now let's talk about something you don't know. Well, a definite composition. Also called the law of constant composition. So this has to do with that whole concept again about mass being conserved. Okay. So, and I want you guys to kind of think about this in different ways. So when we talk about, let's say, for instance, H2O. Okay, H2O. That has how many hydrogens? 2. It has how many oxygens? 1. So we know that it always has 2 hydrogens and 1 oxygen. We know that the mass of hydrogen is going to be roughly about the same. I'll put that a little bit different, right? And so we know that the mass of that hydrogen to the mass of the oxygen. So if you guys look at the periodic table. Periodic table. So this is hydrogen. This here that there represents its mass. Okay, so its mass is about 1. Okay, now, oxygen's mass is about 16. Okay, so we know that if we have 2 hydrogens, that's a total mass of what? Each one is worth 1, 2, right? And then we know that oxygen is 16, right? Altogether, it adds up to 18. So regardless of how many waters I have, right? That mass of 1 water is always going to be 18. Okay. So if I have 50 waters, 1 hydrogen is going to be what? It's going to be 1, right? Okay. So 1 water is going to be water. 18, right? 18, right? So we know that it's always going to be 18, right? So if I have 50 waters, right? I know I can multiply that by 50, and that would give me 15 times 18. That would tell me how much that water weighs. I have 50 waters, right? Okay, so in other words, you're always going to have consistent, defined values, right? For that mass, okay? But also that means for the same thing. We know that water, which is defined as H2O, always has 2 hydrogens, 1 oxygen. Okay? It's always going to be 2 hydrogens, 1 oxygen. If it's this, is that water? No. No, this is hydrogen peroxide. Here, hydrogen peroxide. Okay, so that's going to have a different mass, right? it's going to be something different. Okay. Are you kind of clear with me on that? So, in other words, its composition is going to be exactly the same, H2O, right? And so it's just going to be a multiple of H2O, the number of waters that I have, right? Which makes sense, right? I'm not saying anything that's new or different. Okay. Okay. We talked about charges, right? So a lot of chemistry deals with static electricity, right? That positive and that negative charge, right? So we have a positive and negative charge. These are going to be positive and negative. So if I put two positive things together, they're going to repel each other, right? Have you seen two positive together? Two positive people together? Oh no, honey, you go. No, no, honey, you go. No, no, honey, you go. No, honey, you go. And then so nothing ever gets done, and they kind of get on each other's nerves, right? And they just like, you know. And then two negative people together, same way, right? I hate life. I hate life. I hate life. They're unhappy all the fucking time, right? So then they split up, right? But if you get a positive and a negative, perfect fit. One's positive, one negative. Oh, you're sad. Oh, let me make you happy. You're happy. Oh, you know, I'm sad. Oh, you make me happy, right? So you get that nice little fit. Okay. So opposites are going to attract. Things that are like charges are going to repel. Okay. Make sense? Kind of makes sense in life too, right? Like you never thought about it, but it actually does, right? Kind of balance each other out. As long as they're not too crazy, right? Tell you some stories. Let me tell you. Okay, this is one of those experiments you guys can do at home. You know, you guys have a silk cloth, a fuzzy tail, take a cat, you know, grab the cat by its tail. I've tried it before. They didn't like it too much though. So you just take a glass rod, because what happens is in one case you leave a negative charge, and another case you leave a positive charge. Yes, exactly. Yes, that's exactly the same thing. Yeah. So. Okay, we've talked about chemical equations. You guys are so far ahead, you know. Now let's talk about energy, right? So you guys already know the difference between the reactant side, the product side, reaction side, product side. Okay. You guys already know how to balance chemical equations, right? In there. You're gonna do it like here, like whip it out, right? So here, this is an example of a chemical reaction, but we're also doing in energy. Energy is always part of the game. Energy is conserved, right? So a lot of times energy is stored up in its bonds, right? In chemical bonds. And so if we release energy from those chemical bonds, it's considered to be exothermic. Exothermic meaning energy is being released. Exo, released, okay? Okay, so there are a couple of forms of energy. We're going to talk about energy quite a bit. So energy is generally defined as the ability to do work or to transfer heat, right? That's the very basic definition, okay? The ability to do work or to transfer heat. That's energy. Okay, so here we have butane. And butane stores its energy in its bonds. Now, if we break those bonds and allow them to reform, we can release that energy. And that's what happens here. In reality, that's what's happening. You guys already know how to balance this chemical equation. We've done it like 4 times already, right? Kinetic energy. Kinetic energy is, what is kinetic again? Motion, right? Okay, so then it's the energy due to what? Oh, to movement. That's right, to movement. Okay, potential energy. Potential energy is the energy that is due to arrangement or positioning, right? So if you're on the top of the mountain, right, and you're going to dive off into the water, right? So being at the top of the mountain, you have a lot of potential energy, right? As soon as you jump off, then you start going into that kinetic energy, right? Hopefully you don't hit a rock and you make it into the water, right? Because otherwise, all that kinetic energy is gonna make it splash, right? Well, it's gonna make it smash either way, right? So due to arrangements or bonds, right, we have potential energy. As soon as you start flipping those bonds or modifying those bonds, then that potential energy becomes chemical energy or kinetic energy. Right? So if we put energy into a system, that's called endothermic. So exothermic means
The release.
released, right? So energy is being released. So if we look at it, look at the equation. If it's being released, it's on the product side of the equation. So you're getting energy. So let's think about this. I want you to think about this. I'm burning a log. Burning a log, is that going to be an endothermic reaction or is that going to be an exothermic reaction? Exothermic reaction. Now you standing next to that fire that's burning, is that going to be an endothermic reaction or is that going to be an exothermic reaction? Endothermic, because energy is coming into you, right? You're feeling that warmth, right? You're like, "Ooh, let me get close to the fire on a cold night, right? Okay. Okay, so now mass and energy, right? They're both conserved. There's also E equals mc squared. E representing energy, M representing mass, C representing the speed of light. So this is basically Einstein's potency. You'll also see it written as E equals 1/2 mass velocity squared. Okay, that's another equation. Okay, now if we're just looking at the speed of light, the energy associated with the speed of light, it's going to be dependent on the mass of what we're talking about, right? So if we're talking about the photon, right? So the mass of that photon is going to be the energy. It's going to be the mass of the photon times the speed of light, which is 3.0. Right there on the board. 3.0 times 10 to the 8, and it's meters per second. That's the speed of light. So that's the speed. It's always going to be the same. Okay. So Einstein basically figured this out. And he says, okay, so regardless of what it is, the mass of it times the speed of light, that's going to equal your energy. Okay, so now I want you guys to think about this. So let's see. If I have this fluffy toy, right? And I decide to throw it at Isaiah. So I decided to throw it at Isaiah, right? And I have this jar, and I decided to throw it at the same speed. Which one's going to have more energy behind it? The jar or the fluffy toy? I want you to think. Which one is it? The jar. Okay. So which one's going to have more energy behind it?
The fluffy toy.
Sure.
Yeah, 'cause it's lighter, so it's going.
Energy. We're throwing it at the same speed, right? Throwing it exactly the same speed. So I just throw it all at the same speed, right? Which one's going to have more energy behind it?
The jar because it's heavy.
The jar because it's heavy, because it's dependent on mass, right? So if they're both at the same speed, right? The jar is going to be heavier than my fluffy toy, right? Okay. So, but I could throw this faster, right? Fast enough so that it would have more energy, but I have to throw really fast to sit there and impact, right? Because again, it's dependent on mass. So that basically means that as mass goes up, what's going to happen with the energy if the velocity is kept constant?
You record the.
The record?
I have to go to the.
Okay.
Yeah, thank you.
Okay. So I said, as mass goes up, what's going to happen to energy if the speed is kept constant?
Stays the same, right?
Is it? If mass goes up, so does energy, right? Because they're directly, what we call directly proportional to each other. As one goes up, the other one has to go up too, right? So if our speed is held constant as mass goes up, in other words, if it gets heavier, right, and I'm throwing it at the same speed, it's going to sit there, and one thing, it's going to hurt a lot more, right? Because there's going to be a lot more force behind it. So the energy is going to go up, right? Okay. So as mass goes up, energy goes up. Okay. So if I say I have two fluffy toys, right? I throw one like this. Okay. You're supposed to catch it. He's like, I'm trying to take notes. You stop throwing stuff at me. Okay. And then he decides to throw it back at me like that, right? Right? Who's gonna have more energy? Like that? Yeah, he's gonna have more energy, right? Why? He had more force behind him. He also had more speed, right? It was faster, right? So they're also going to be directly proportional, although his is going to be worse because it's twice the amount. It's squared, right? So his impact is going to be worse than my little mass because it's the same thing, right? It's being squared, okay? So that's also considered to be directly proportional. It's also exponentially proportional too, right? It's double win, okay? So those terms you guys need to get familiar with, directly and indirectly proportional, okay? So let me give you another example.
At the very end.
Oh, that's MS.
MS?
M over S.
Okay.
Okay, I have third grade handwriting. You got to deal with my third grade handwriting.
And that is with the speed of light?
Speed of light, meters per second. MS. M divided by S. Okay. If you guys just see M, that usually means mass, right? Mass, velocity, right? Okay, and this one is mass times the speed of light. Okay, so things are considered to be directly proportional if they're going up with it. It's considered to be indirectly proportional if it's going down. So let me give you an example. Let's say we can actually use the same equation. Okay, so if we say that energy is going to be held constant, right? Energy is going to be held constant. So we're basically going to say we want the same amount of energy, right? And if I increase the mass, what has to happen to the velocity if energy is going to be held constant? Does it?
That's cool.
Okay, let's think about this, okay? So let's say we want energy to be 100. Okay? So E has to equal 100. Okay, so we're saying energy is going to be 100. Okay? So, and then if I say, we'll use this equation here. Let's say I have a mass of 1. Okay, so then V has to be what? If I solve for V. So I have 1/2 times 1, and that's going to equal 100. If I solve for V, so then that's multiply both sides by 2, right? So then that's 200. So then I have V squared equals 200. So I take the square root of that. So then that's going to give me 10 square root of 2. Right? That's what's going to be. Right? Okay. Now let's say we increase the mass. If I increase the mass to 10. This is the case where M equals 1. Okay, so now I'm going to increase the mass to 10. So would we expect V to be higher or lower? Okay. We would expect, because mass is increasing, the velocity should be going down. So that would be inversely proportional. So mass to velocity is inversely proportional, where mass to energy is directly proportional. Directly proportional meaning that both go up. Indirectly proportional meaning one goes up, one goes down. Okay, so if we plug this into that equation, so we get 1/2 times 10 Okay, we solve for V again. So in this case, we get 200 divided by 10, so that's 20. V squared. So then V is going to be the square root of 10. Square root of 20. So which is 225. Okay. Okay, how many of you guys are? Don't worry, we'll get you caught up. Go to your calculator. On your phone. Turn to the side. How many of you guys have iPhones? Turn to the side. Your calculator will look something like this. All right. So you can see all of the special functions. So do me a favor, hit 2, then hit times, and then put 5 square root. That's what the square root looks like. This says 2. It looks like that. Okay, so this guy is equal to 4.7. And then in this case, so in the other case, if you go 10 times and then 2 square root, and then that's going to give you 14. Okay. So if my mass was 1, right? My mass was 1. I got 14.14 for my velocity, right? Okay, so as I went from a mass of 1 to a mass of 10, which is 10 times greater, right? Isn't that greater? So that means that the mass is going up and down. If I'm going from a mass of 1 to a mass of 10, mass of 1 to a mass of 10, is my mass going up or down? It's going up, right? Okay. Now my velocity at a mass of 1 was 14. You guys see that? Now my velocity is going from 14 to 4.47. Is that going up or going down? Okay. Okay, so since these guys are on the same side of the equation, as one goes up, the other one has to go down if my energy is going to be held constant. Guess what I mean by constant? The same, right? So I'm keeping my energy exactly the same. I'm not changing the energy. So for me to keep that energy the same, something has to happen. If the mass goes up, that means the velocity has to go down. Okay? So they're going to be indirectly proportional. So as mass goes up, mass going from 1 to 10, opposite directions. Okay? Because they're on the same side of the equation. Right? And they're not divisible by each other. Right? Same side of the equation, and they're not divisible by each other. Okay? Are you guys with me so far? You guys have a look. It's just that math part, right? It's that math part, right? Okay, but it does make sense, right? Because look at it, the numbers, right? And I went from 1 to 10. If my energy is held constant, right? I'm keeping my energy the same. The only way that that's going to be the case is if my velocity decreases. My velocity goes from that 14.4 to 4.7. That's the only way that can happen. Keep that energy the same. So if I decided I wanted to go up, let's say another, 15, right? In terms of mass, what's going to happen? If I went from 1 to 15. Velocity, is it going to go up or is it going to go down? It's going to go down. That's right. Okay. So if my mass is going up, my velocity is always going to be going down. Okay. If things are held constant, if the energy is held constant. Okay. Now we can flip it, right? If I increase my velocity increases, what has to happen to my mass? It has to decrease, right? So they're going to be going in opposite directions if my energy is held constant. Okay, so that means it's indirectly proportional, right? Goes up, then it has to go down. Okay, and that's going to be kind of important. You guys are going to hear this again and again and say, oh, they're directly proportional. Oh, they're indirectly proportional. And you guys got to remember, directly proportional means that on both sides of the equation, this side of the equation, this side goes up. So, indirectly proportional, opposite directions. Okay. Okay. Don't worry about it. You'll get another opportunity here in a minute to talk more about directly and indirectly proportional. Okay.
I just have a question.
Yes.
About the calculator part.
Yes.
How did you get that for?
Oh, so when you enter it, you want to enter it as. Let me see if I can get my handout correct. I'm going to play with toys today. So when you enter it, you want to enter, the first thing that you want to enter is, let's say, the 10, and then you want to hit times, and then you want to hit 2, and then you want to hit square root. Okay? Is that the value you got? And then square root. Because you're saying that I'm taking the square root of 2.
What button are you putting on your iPhone?
What was that?
What button are you putting on your iPhone?
There's like 3 different square roots.
Square root alone, but it's gonna be like.
It's the one with the Y and X.
Okay, so
That's what I thought.
that there's the square root. So it says on the iPhone, it looks like this. So the square root button, it tells you because you get either have a cube root. You could have 2 here, right? So that's square root. Or you could have cube root, which has a 3 on top. So they want to make sure that you know the distinction, right?
Yeah.
Okay, so when you hit it, when you enter it, so what you do is,
Yeah, how do you enter it?
okay, hit your clear button first. Clear? So then the first thing that you want to do is hit 10 times, and then you want to hit 2, enter the 2, and then you want to hit the square root button. And then you hit equal.
Oh, then, okay.
Because if you don't hit the equal, it doesn't do anything, right?
Oh.
Yeah, you didn't hit the equal. Everybody forgot to hit the equal. You gotta hit the equal because that is just like answer. So did you guys get 14.14? Yeah. So I have to remember that because, you know, this sounds weird, but most people, they get the math part of it, right? And then when they enter in the calculator, they fuck it up totally, right? By not hitting, and I'll show you some little tricks, and I'm really good at using little tricks. Okay, now do the same thing for the second one. Yeah, 2 square root of 5. For those who didn't get it.
Okay, that was so easy.
Okay. Okay, you guys are good? Okay. You guys ready to move on to the next level? Oh. Okay, so law of conservation of mass, right? So total quantity of mass and energy in the universe is fixed and it doesn't change. So basically what you put in is what you get out, right? That's going to look for mass and that's going to look for energy. So we have to be able to account for it. Now, the thing is that as much as we want to account for some things, sometimes we lose things to the system. It's not that it's not accounted for, right? It's just that we haven't learned how to account for it. Okay. So at the end of the day, it has to be conserved. What you put in, you have to get out. Okay. So, law of conservation of mass just basically says the total mass of reaction in a chemical change is going to be equal to the total mass of the products. So in other words, if you put in 150 pounds in your reaction, guess what you should get at the end of the reaction? 150 pounds. Okay. Law of conservation of energy. The quantity of energy within an isolated system doesn't change. So if I put in 175 joules, guess what I should get out? 175 joules. Okay. So at the end of the day, it basically says that the energy in a system, in a conserved system, is neither created nor destroyed. Okay. So it's just going to be changing forms, right? So that's the same thing with mass, and that's the same thing with energy. Okay. Now, there is one exception. I'm going to write this down. One exception. And we're going to talk about it early this time. You can't wait till the very, very end of the semester to talk about it. We're going to try to talk about it early. The one exception is nuclear energy. Nuclear energy is the one exception. Now, that one is going to be a little bit different, right? And it's conserved in its own right, but it's going to be conserved differently than how we think about the conservation of mass and the conservation of energy. Okay? And we'll talk about that distinction later. But we are going to talk about it earlier this time. Okay, so what we're going to do is, do you guys mind if we take a 15-minute break? You guys okay with that? 15-minute break. So normally, today we would normally do a lab, but today we're not going to do a lab. We're going to do the next part of the lecture, because we need the next part of the lecture before we can start the lecture. Okay, so we're going to do a double lab tomorrow, right? So tomorrow is going to be lab, it's going to be a quiz, and then we're going to do lab, maybe another lab, right? Depending on how it's so 15-minute break, and then we'll do more lecture.
Like by the. Oh, You guys don't mind if
Bias. Yeah. You have one? Yeah. Have one? Yeah. That's the problem. It looks like this one right here, hello? I don't know, like I told her right now, that we're coming, it's another class. But that was the last time we had to spend. But, yeah. That's what I asked. Wait to go. Like, they already have everything written down. We have already. But, like, everything. So, different, so. So what? Sign to the. Okay.
I figured out that. Um, Oh, really? Which which was in we just have to go to the people. One with the names, you know, so- Well, I've seen the pictures. I should- Like one of them, I was like, okay, that one looks, and then looks like the girl that sits right here. Me too.
Probably gonna actually make sure for their lab reports, they don't have to.
Yes. Did I not say that?
Yeah, I don't think it's down. The depth of the procedure, I could send them exactly.
Yeah. And it's only, they only had to do a formal lab report. That one.
So I was like, I had to like look at it, so I was like, the other whole thing would be like this. I didn't even get to the whole thing, I don't know. Oh, this is my first time. Oh, okay, they were on this chapter. Little brother was there.
Everybody's doing it here.
Good. You guys can email me your labs before you turn it in, and you guys can feedback on your labs. This will be the only lab I do that for, because your other labs will be exactly the same format. Okay?
Which is the actual. Okay, this is- Oh, yeah, because that's in there. Eventually. Let me show you. I started on my. I just did the results. But-
Unfortunately, there will be no change. I'm not sure if they'll open back up. But it's in there. It's hard. Yes.
Maybe.
Those could be some of the, like, there's like some of the things that you write about.
I. And now you see.
What went down?
Yeah, basically what went down. Other than the fact that when we had to take time, take the floor, and then once we jumped into the. No, one, this is mine.
Oh.
But I went right here to answer. And then chart.
It has a circle.
No, watch. You go to sheets. At least it's keeping me until the next one. Yeah, mine too. I get these other 15, so y'all will be. Yeah. Like, that's what's that. Yeah, give me some time. For real. I need that time. I don't got money. Okay, so I went in here to chart, and then if you click one of these, it'll pop up a random one. So what you have to do is you have to go to from sheets, and then you have to make a new one. And all your reports are here. Or what you can do is go to Google. This is where you would do the two.
Yeah, she did a great job.
Yeah, so then you would just fill it in, and then once you go back to your report, you know how I went here and did it? So you go to insert, it'll be popped up on your chart, so you put front sheets, and then all of the charts that you did. I like that. I was telling her, she was asking me how I did. I did this one, and now that was like time. So I went to actual like Google, and you know, like it gives you the options to go from like your dogs to the sheets. I put sheets, I added a blank one. From here, I went to insert, and I put chart. You can copy or paste, or right here, you're gonna pick which one you want, and then you fill in the blank actual data up here. And then it automatically puts it here. So then when you go to your actual report, go answer chart, pick from sheets, and then you can pull up your charts that you did. See how these are the ones that I did.
You went to Starbucks and you didn't bring anything back? Man, I see where I fall in the ladder of importance there. Package, yeah.
Like, what is she doing?
It's on the. Where's our last one? Yeah, it's on the Google Drive.
Everybody's.
You just see. Oh, you didn't. I could have.
So they're all together.
I was just saying that. Did you drop your phone? The car?
That's like a blue
Outside,
now.
and you just come in where you drop it down.
Oh,
I'm
no.
If you want to think about it. Oh, the scent.
Yeah, but I was putting them on.
I know.
Oh.
But you know,
Hello. No, like.
Hey, guys, I do want to let you guys know, that for your first lab report, this lab only, you guys can email me your labs and I will give you guys feedback on those labs. This will be the only lab I'm doing it for though. Because the other 3 labs you will write up will be the exact same format. Okay?
Okay, cool, that's what I want.
And I'm responding to your email right now. I did send out a couple examples of my labs.
Okay, everybody back? That's great. Okay, so you'll notice that you guys should have 2 handouts, right? You should have chapter 5 and chapter 20. Okay. Don't have chapter 5 and chapter 20?
At 5.
Don't have chapter 20 next? It should have been there.
Oh. Never mind, we got it.
Okay, good. Chapter 5, chapter 20. Don't freak out. Don't worry about it. We're gonna go through the entire book. Don't worry about it. It's fine. You know?
like 4, 15.
I like to move around, you know, there's rhyme and reason to my logic. I don't like the way the book is ordered. And I think, okay, you know, I'm gonna introduce nuclear components, right? I'm like, yeah, let's just go ahead and introduce nuclear chemistry. It'll be just the same, you know, same concept. We're just doing it on a different scale. You know, so just trust me on it. You'll appreciate it in the end, you know? So, okay. So we know what the law of conservation is, right? Everybody's comfortable with the law of conservation? Okay, so. Still here. Okay, so now I want you guys to sit there and think about this process. Okay, so take a look. We have the boiler. Gotta remember. So we have this boiler here, right? Now, first off, we have natural gas. That's gonna do what? What happens with natural gas when you use it? We're heating things up, right? Is that a chemical reaction? Burning of natural gas? Chemical reaction, right? Yeah, chemical reaction. Okay, so we're using a chemical reaction to heat up the boiler, right? So then we take the boiler has water in it, and then we make what? We make steam. Is that a chemical reaction or a physical reaction? Physical reaction. Oh my God, we use a physical reaction to make steam. That steam goes through that pipe, right? See the steam going through the pipe? Okay. That steam then turns that turbine. So we went from, so steam moving. Okay, so steam is moving. Is that what you say? It's moving. Is that kinetic energy? Kinetic energy. Kinetic energy. Would you agree? Anybody disagree with me? Kinetic energy means what? Movement, right? Energy resulting from movement, right? Okay, so that steam is turning that turbine. Is that moving still? Still kinetic energy. So that turns that generator, which makes electrical energy, right? Then that electrical energy goes through the lines. It comes in and powers our lights, our range, our TV. Yeah, it all started from what? A natural gas, which we did to do what? We use it to heat up. Okay, so we use a chemical reaction to get everything started. So everything started from a chemical reaction. We went from a chemical reaction all the way to an electrical energy, right? So during that stage, everything is conserved, is it not? Okay. Everything is taken into account. We covered all of that steam that we were making, right? We made those turns, did everything it's supposed to do. They made that electrical energy. So all of the energy that we put in the very beginning, we got out at the very end, right? So at the end of the day, energy is what? Energy is what? At the end of the day.
Conserve.
What was that?
Conserve.
Conserve, right? Doesn't that make sense? Started with energy, we ended with energy, right? We just changed its form, right? Are you with me? You had that look. You guys had that look. You make me scared sometimes. Right? So I sweat a little bit. I'm starting to sweat. You know, getting all hot and bothered here. Not in a good way, you know. Huh? I'm giving you guys anxiety. Good. So it's what? These are the fundamentals of chemistry. Well, if I can get this thing to work, it's not gonna work today. Let's see. I think I just crashed my laptop.
Guess we gotta go home.
No. We're talking. We're talking. There we go. Welcome to chemistry, right? That's the big thing. These are the fundamentals. This is chemistry. That's it. Right? It's not too much to it. Now, don't get hung up on the math. Don't let the math scare you, right? You guys will make it through the math. We'll get you guys through it. Okay, but you gotta put in a little time because I know that you guys are rusty. That's usually the rustiest part once you guys are at is the math, right? So we get through that math, we'll be okay. Okay? Easy. Easy peasy, right? Piece of cake. Strawberry chocolate. I'm just letting you know. Okay, so let's start on chapter 3. Now, I go off the tracks, just so you guys know. We'll start here on the slides and then we'll move to something else. Go ahead, chapter 2. Anybody missing chapter 2? Did I not give it to you guys?
Maybe all blue.
Everybody got chapter 2 with no chapter?
To be certified.
Did everybody have the lab number 3, right? Huh? Oh, was it you? Oh, you need lab. Okay, so lab number 3 is for tomorrow. Lab number 3 is for tomorrow. We're gonna add one more experiment to it. I'll be printing it up tonight, and that'll be added on to lab number 3. Then we're gonna do lab number 3. Okay. So tomorrow's gonna be a 2, right? Quiz and 2 labs, right? Maybe 3.
Okay.
Hey, I'm ambitious, you know? Okay. Okay, so we're gonna start off with scientific notation. We'll go slow, work you guys back into it, but we want you guys to kind of get used to what we do as scientists and how we like to write it. Okay, let me just boil it down to you. Scientists are lazy, right? Like most of us, right? We don't want to do any extra work, right? So we want to try to find the easiest way to write things so that we don't have to write a whole bunch of zeros. Have you guys ever wrote things that had 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, you know, we don't like doing that. You know, have to, right? So we use scientific notation to try to help us with that process. And the way that we do it is that we use this format. We use A point B C D times 10 to the exponent. That E represents the exponent. Okay, now this is called, again, scientific notation because, again, we're scientists, we like to name stuff after ourselves. We wanted you to know that this is the way we like to do things, keep it simple. So we like to have one digit, that A, right? And then we put a decimal. And then if we have a couple of numbers, let's say we have 4 numbers afterwards, we put those 4 numbers, right? And then we multiply it times 10 to whatever power it is. Let me give you an example. So if I have this number, okay, you guys see that number? Is it too small? I'm going to make it big. Okay.
I think we missed 2 zeros.
What's that?
I didn't think you're missing a few zeros.
You think I'm missing a few zeros? Not enough zeros for you? Okay. So now if I had this number, that is a shitty number to have to write all the time, right? And you have to keep track of it every time on the line or something like that. We don't like doing that. That's too much work, right? So we like to try to keep it simple. And so we'll change the way it's written, right? So what we'll do is that. See where this decimal point is at right here? Okay, so we're just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So we get to that very first digit, right? So then we write this as 6.432 times 10 to the minus 15. Okay, so because this number is so small, right? It's less than 1. Would you guys say it's less than 1? Right? It's really tiny, right? So we know that it has an exponent that would be a negative value. Okay. If it's a number that's greater, much greater than 1, right? Then the exponent is going to have a positive value. Let me give you another example. Bless you. Okay. So enough zeros for you. Okay. So in this case, we have to start at the very end, right here. That's where our decimal technically is at. And then we're going to move over. That's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8, that's 9, that's 10, that's 11, that's 12, that's 13, that's 14, that's 15, that's 16, 17, 18, 19, 20, 21, 22, 23. So that'll be 23. So then this would be 2.034 times 10 to the you guys see that? Okay. Now, again, it's to our benefit to write it, right? It makes it so much easier for us. So you don't have to carry around all those zeros. Because I carried around all those zeros. And particularly when you're talking about atoms and stuff, right? When we talk about an atom that we can actually, let's say, we're looking at carbon on the table, right? That's going to be, 10 to the 24th, 10 to the 25th atoms, right? So it's going to be a whole bunch of atoms, right? And so we need to be able to sit there and be able to write it down simply without having to carry all the zeros. Okay? It's not too hard. Everybody sees it. Now you'll notice, again, this is positive. This value is a whole lot greater than 1. So we want to kind of pay attention to that, whether it's a negative exponent or if it's a positive exponent. That tells us whether it's a really small number or if it's a really large number. Okay, everybody with me? Am I telling you anything that you haven't seen before? And if you have, don't worry about it. Tell me now so that we can get to it. And again, there's no shade in anybody's game right now, because right now we're all trying to learn this together. And I'm gonna, if you tell me everything's cool, we're gonna be finished with this chapter tomorrow or today, later on today, right? And then I'll start chapter 5 today.
I still don't understand how you get like the negative and the positive.
Good. Okay. So the negative makes reference to the size of the number. The decimal here, and if we're moving in this direction to get to a whole number, right? So we're moving from left to right, right? So if we're moving from left to right, then that means that we're going to have a negative value. If we're moving, if we start at the very end here and we count up to get to our our single number here. Then we're gonna be, it's gonna be a positive.
Oh.
Okay, thank you. Okay, everybody's good with that? You understand that positive and that negative? Bless you. Okay, so this basically just tells you how the book wants you to sit there, right? And it's a quick way of remembering it, you know, and everything like that. And so again, you're just going to be looking for those non-zero numbers. You want that very first digit, right? That very first digit, the non-zero numbers. That's what you're trying to get to. So you're trying to get there either counting that, right? So let's see if you guys can use that. So here's some examples. Convert 3,672,192 to scientific notation. And if you guys can do me a favor, right? So instead of writing it all out, let's do it so that we only have 4 digits. So set it up so that there's only 4 digits. A total of 7.
That's already solved.
I know, because I give you guys the notes, you take a whole thing, but you can still do it. You know, you can do it on the side there. I want you to figure it out. I know it's solved, but I give you the answer, so just in case I'm not there to walk you through it. You know, I'll stop doing that.
No, I was just saying.
But actually, it's not solved the way I want you to solve.
Okay, do only want 4 digits.
Okay, everybody got the first one?
Yeah,
4 digits?
yeah.
Because I only wanted 4 digits, right? So I want it, instead of having, how many total digits are there? 7. So instead of 7, I just want 4. So I want you to write this number so that there's only 4 digits. Right? Now, you're not including the exponent. The exponent isn't counted towards these digits. We haven't got, we're getting there. Just relax, relax. We're getting there. We'll be talking about that today. You're just so anxious. Yeah, I figured I had to do that.
Don't.
And I'm actually-
So it's not like an actual like,
It's gonna be
So for the bottom one, you want 4 digits as well?
No, that one. If you can give me 4 digits, you can. There's ways you can do it. I just want- Okay, so let's talk about this first one, right? So I said I wanted 4 digits. So where am I gonna start at? I'm gonna start at that 9, right? And then I'm gonna count which way?
To the left.
Okay, 1, 2, 3, 4, then my answer should be
3 points.
3.672
Oh, okay.
times 10 to the what?
Okay.
10 to the 6. Okay, so normally if I say I want 4 digits, I'm going to take that number there. And if that number is greater than 5, right, I'm going to round this number, right? If it's less than 5, I don't round it, right? I'm just going to leave that number alone, right? Okay. Everybody get that? Okay, now I'm going to add another layer to that. You guys ready for another layer? Don't start doing this yet. It's still early, right? Let me add this other layer. Okay, how many of you guys ever been on a teeter-totter? In a teeter-totter, seesaw? You know? Okay, seesaw, right?
Yeah.
Okay, so 5 is that seesaw, right? So if it's exactly at 5, right? And let's say they're both the same numbers on both sides, right? They're gonna be totally even, right? Totally even. If this number has 0.00001 added onto it, it's no longer gonna be even. It's gonna push it over, right? It's gonna tilt it. It's gonna cause it to be heavy, right? Okay, so 5 is our kind of in our inflection point, right? So if it's exactly 5, then we're gonna leave that number alone. If we have any numbers following that 5, then it's gonna shift it over. So let me give you an example, right? So I said that we're gonna look at this number here, right here. Right? So if this wasn't a 1, right? Let's say it was 5 exactly. Right? And then it said 5, 0, 0. Right? So since this was 5, 0, 0, it's kind of like that inflection point, right? And we're looking to whether or not we're going to round this up or whether we're going to leave it alone. Right? If it's 5 perfectly, we're going to leave it alone. Right? We're not going to round it up. Now, if it's 5, let me write down the number so you guys can see what I'm talking about. So if it was that, right? So, and we're going to use this number to decide whether we're going to round this number up or below. So if it was 3, 6, 7, 2, 6, 0, 0, and we only wanted 4 digits, right? Is this guy going to be rounded up? Yes. So then we would know it would be 3.673 times 10 to the 6, right? Okay, where this guy, since it's 5 perfectly, this guy is only going to be 3.672 times 10 to the 6.
So it doesn't have to be like after the 5 and 999, it has to be even just a 1.
Yes.
You would wrap it.
That's right, exactly. So, see, we're right on top of it. So if I had 3.67725 0, 0, 0.1. Am I going to round up? Or am I going to leave it? 5. So it's going to be 3.673 times 10 to the 6. Because what you just said, right? Because there's that little bit of speck, right, afterwards that makes it up, right? Everybody get that? Anybody not get that? It's those subtleties, right? So 5 even. So 5 perfectly, right? But if I have a little bit more, it's just going to push it up, right?
Just say, just give me an example, have a better one. Because there's no
Let me give you another. My water bottle. So 5 is that point where it's completely full, right? If I go 1 drop over, yeah, right? So that's what we're doing. It's like going at 1 drop over. Okay? Does that make sense? You guys kind of got that? Okay, good. So our next number. Everybody got this down? Did you get a picture of me? That's good. That's okay. Okay. Hurt my feelings enough. I'm gonna start crying here soon. Okay, so the next one, the answer is going to be, where am I going to start? At the decimal. Okay, which way am I going to move? Okay, so that's 1, that's 2, that's 3. So 4.6 times 10 to the left.
-3.
-3. That's right. Why is it negative?
because we came from.
That's right. We're that way, right? All right, this way. Okay, good. Okay, questions? Concerns? Cash? Kool-Aid? Okay. Okay, so now, because not all of us are disciplined enough to write scientific notation, sometimes some people will write in scientific notation, sometimes people will write in decimal points. Sometimes you have to be able to do both. And remember, I told you guys you're gonna have to translate, right? Because most people don't know what scientific notation is, right? Notation. So you want, 3.5 times 6 and 7, and they're going what the hell is that? And so their eyes are gonna glaze over, kind of like what you guys did to me in the very beginning too, right? And so, but you're gonna have to be able to translate it, right? Oh, this is what that is, right? So you're gonna have to be able to go both ways, right? And so let's see if you guys go both ways. So I want you guys to convert this into decimal form. Don't cry too much. And I know the answers are on the sheet. Try to do it without looking at the answers. You did it on purpose. Okay, guys ready? Okay. So we have 3.47. Let me start 49 times 10 to the negative 11. Okay, so How am I gonna write that into? Decimal form?
To the left.
To the left?
Yeah.
So you guys are saying. Sure, I understood. Slide this over here. So you're saying I'm gonna take the decimal and then go. That's 1.
To the left, left.
11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's where my new decimal is going to be.
Yeah.
Okay. And then all of the rest of these are zeros. 0, 0. Zero. That's 0, right? So that's this part right there. Okay. That what you guys got?
Yeah.
Okay. Now what about the second one?
To the right.
One to the right? Okay. So 5, 6. 7 to the right. 1, 2, 3, 4. So 0, 0. It's going to be now.
We don't have to write the 0.
You don't have to write the point 0,
Okay.
but you can. So I like putting the 0 in front so that I know. 'Cause I always, if I don't see a 0 in front of it, I assume that there's a number sometimes. I don't, or I'll have numbers out like next to each other. That way it helps visualize it. Okay, questions? Concerns? Straightforward, not too. I know, simple, right? Okay, good. Now, you should be able to do this with your calculator, right? Can everybody do this with a calculator? Yeah, everybody has a phone. Pull out your phones. Okay, so the way that we do it with our calculator, there's a key that has EE or EXP. Some of you guys actually have 10 to the, and usually you have your iPhone, it says EE. Okay. So now this is one of the most common mistakes that are made. When you're entering this number, right? So let's say we're going to enter 2.753 times 10 to the 27. That's what we're going to enter. Okay. So the way that you would enter that is you'd enter 2.753, then you press EE 27. Okay, so let me type that out. 2.753 EE. Press the EE button to the 27. Okay. So did it give you what you were expecting? That's exactly it. Yeah. So when you look at it, it'll say 2.753 E 27, right? That E represents is times 10 to the 27. Okay. Now let's say we wanted to multiply that by, so go ahead and hit times. Let's do 2 point. Check. 713 times 10 to the negative 41. Actually, let's just keep it simple. Let's go 75. Yeah. Times 10 to the negative 41. Okay, tell me what you guys got. What did you guys get?
2.753.
Okay, so now when you have that negative, right, it's not going to be the negative sign. It's going to be, there's another symbol that's plus minus, or sometimes it'll be minus in parentheses. So it'll look like this. It'll either look like this, plus slash minus, or you're going to see minus in parentheses. And usually it'll be like next to the decimal or something like that, depending on your calculator. Okay, do you guys see that? So when you enter it, you're going to enter for your negative value, you're going to enter 2.735 EE.
It's my 3.
I'm sorry. Thank you. Told you sometimes, it's because it's a Monday. It's got to be a little bit serious. Plus or minus. So then it should give you a negative value, and then you enter 41. Or you can enter 41 plus or minus. It should look the same. Okay. So what did you guys get? Okay. Okay. Now, if we multiply that by that first value, what did you guys get?
First one? Yes, negative 40.
That also- Yes,
Wait, so are you guys multiplying it? Or are you just doing the new one? Because I'm multiplying them. You just go back to 0.
Oh, it's this one?
Hey, what did you guys get? If I did this part. Yeah, 0.7. Okay, so if I have 2.753 EE to the 27 times 2.753 EE to the negative 41. Okay, and you got how many zeros? So if you turn it right side up, so 7.57 times 10 to the negative 14. Your E's not working? Let's see. Oh, that's a difference. This is a special type of. Okay, so you have a different type of calculus.
And now the type C, oh, see, that's not right.
Yeah, we have to get a calculator. You have an iPhone? Yeah. There's another word to it. Let me see. Usually there's another value. EX.
Yes, that's what I'm getting. Shoot.
Super purified 3 times.
Yeah, we're gonna-
Okay, gotcha.
Yeah.
Yeah.
Yes, you should have your scientific calculator. I'm just showing you how to do it on your phone because it works the exact same way on your scientific calculator.
Everybody.
This was our senior year.
And usually there's an app. We'll see if I can find one for you. Yeah, because there's an app that.
The presidential.
Yeah, yeah, so you guys don't want to mistake the lowercase e. If you guys look on your calculator, there's this little e. Right? There's that little e. So that there is a different type of exponential, right? It's a special e, okay? So you have natural log, right, which is ln. And then the opposite of natural log, or the exponent of natural log, is e, okay? And it has a special value of 60. So they're not the same thing, but when it shows up, when you have that little e and that number, that shows you your exponent. It just means the exponent. Is everybody clear on that? Okay. So, and I'll find that app for you. So I'll try to get it for you tomorrow. So you won't be too far behind. But you can also, if you guys get a standard scientific calculator, you can check them out from the library for the whole semester. You can get a graphing calculator, or you can get just the standard scientific calculator. Either one of those will be fine. I strongly recommend, because you can't use your cell phone on the test. Yeah, but I'm showing you on your cell phone because usually that's what we do when we do our homeworks, right? Okay, let me go to that. And then plus it's the same thing that you have on your scientific calculator. Yeah. Okay. Okay, so let's move forward. Okay. Okay, so now this is going to be kind of important. Right? So quantity. Now, quality and quantity, right? And quantitative quality, right? So qualitative isn't giving us values, right? Qualitative is saying, oh yes, you're relatively big, right? Teach you guys in this class. Everybody says yes, right? Yes. So I would say everybody said yes, right? Quantitative is rate this class from 1 to 10, and then we're going to add up the scores, right? So quantity is going to be where we have a value and a units, because we have to sit there and tell us the units, right? Because let's say, for instance, I say, come back in 5. Right? Won't you come back in 5? Is that 5 seconds? Is that 5 minutes? Is that 5 hours? 5 days? You know? So if I just say come back in 5, you have no fucking idea. You just know it's 5, right? Right? So you want me to know the units as well, right? So I want you to come back in 5 minutes. You got 5 minutes to go to the bathroom, you know? Or you got 5 minutes to take this test, right? 5 minutes. Okay, minutes is what? What was that? Is it minutes and seconds? Minutes and 60 seconds. Oh, well, you mean I can convert my minutes into seconds, right? But those are all units of what? Of time, right? So we know that minutes is units of time. Days are units of time, right? All of those are units of time. Minutes, seconds, hours, days, years. Come back in 5 years. When you get your shit together, you can come back in this class, right? The 5-year break, yeah. Nobody wants that 5-year break, right? There's tons of other things that can be happening in those 5 years, right? So when we talk about quantity, quantity is both that value and the unit, right? And it's important for us to tell me the units. Because if you just tell me 5 could mean anything, right? You'd be a little pissed off if I told you come back in 5 years from now. I want you to come back here. You'd be mad, right? You're like, I'm not gonna let you take my class until 5 years pass. You're gonna be like, go somewhere else, right? You're a little upset. He would not let teach his ass. I'll go somewhere else, right? Spend my money somewhere else, right? Okay.
I'll come back if I need
They come here 5 years and well, if you take that long to take this class, then that's a whole other topic we need to discuss. Okay, so unit is very important. If you don't have those units, it don't mean much. Okay, so anytime that you're writing an answer, you should have what? Units, right? Because if I tell you I want 50 mils, that tells you what? mLs. I want 50 milliliters. But if I just said I want 50, you're gonna ask me 50 what? $50? Yeah, I'll take $50, right? But I want 50 milliliters, right? I want you to put 50 milliliters in there, right? Would you put 50 liters? Would you put 50 gallons? No, you're gonna put 50 milliliters, right? So those units are gonna be important. If we don't know those units, we don't know what the hell we're talking about, right? And so it's important for us to understand what units are and what they mean, right? We talked about volume. Volume, milliliters is volume. We know that volume is what? Volume. It's length times width times. That's the fucking equation. What does that mean? It's centimeters cubed. You're giving me units now. Those are beautiful. I love those. Those are units. But what does it mean? What was it? It's the space. It's the space that's being occupied by, right? That's what volume is, right? No. It's fine. It's great to know equations, but that doesn't mean shit to us. Equations don't mean nothing if we don't know what it means, right? And that's what I want to get across to you guys, because you don't know how many people I'm telling. Okay, so we're gonna go ahead and measure the distance, and they look at me like, distance? What the fuck's that, right? And you think I'm kidding? No, I'm serious as a heartbeat. But if you don't know what it means, it don't mean nothing to you, right? Right? What is distance?
6 feet, you know? COVID.
The station during COVID, yeah, 6 feet, right? So we know that distance is going to be space, in this case, between me and him. That's 6 feet that we need to keep away from each other, so he doesn't get COVID, right? Or I don't get COVID, right? Okay, so we know that that's distance, right? We know that seconds is time, right? We know that feet is length or distance, right? We know that gallons is volume. Okay. We know that pounds is weight. Okay. We know that grams is its weight. Okay, good. Okay, so those are going to be important. Units are always going to be important because if we don't know what the units are, we don't know what the hell we're talking about. Right? So let me give you an example. How many of you guys are on Tinder? Just go ahead and date. How many of you guys have ever been on Tinder or whatever? Some dating app, right? You name your dating app, your dating app of choice, right? Okay, Bumble, okay. So you go on Tinder or Bumble and everything like that. You see my ad, I'm all spruced up, and I say I weigh 100. 100, right? First off, you look at me and you're like, yeah, you weigh 100, right? Because we're thinking about 100 what? Pounds, right? But I may not be thinking about 100 pounds. I may be thinking about kilograms, not kilometers, kilograms, right? So I weigh 100, right? It's not a lie. I weigh 100 kilograms, right? Yeah, because they're not paying attention. Whose fault is that? It's not my fault that they pay attention to the unit. They failed. Yeah, they should have paid attention to the units, right? I'm not lying. But first off, you're saying you weigh 100 pounds. As a woman, and a guy tells me he weighs 100 pounds and he's supposed to be so tall, I'd be a little worried. I'm like, crackhead. First thing that comes to my mind, right? I'm like, a guy weighing 100 pounds and he's 5'9", 5'10". No, there's no way. Crackhead. Right? That's the first thing that comes to mind if it were me, right? And so I'd be like, nope, So units are important, right? Are they not? You kind of see where they're important, right? And then believe me, when you sit there, like I travel internationally, right? And I've been single when I travel internationally. I've been in industry, so I travel a lot. It's twice a month I travel, right? When I travel, from the single sites, I'm single now, right? I'm turned up, right? And, and I'm like, huh. And then I'm thinking, they're talking about kilograms. I'm like, kilograms. Oh, she's nice and fit and everything like that. And you meet her and she's like, big old booty, right? You're like, wait a minute. That was unexpected, right? Not at all, right? But we still had a good time. I was having a good time, So I'm like, okay, so you pay attention to those units, right? Do you not, right?
I'm like, you said you were 100 kilograms.
Yeah, so anyway, units are going to be very valuable. So we need to pay attention to them, right? And so for many reasons, right? Even dating, right? Okay, so let's talk about this. So if we have 50 minutes, we know that how many minutes are in a second?
60.
How many minutes are in a second?
How many minutes? 1 minute.
1 minute and 60 seconds.
Okay, so we have to be careful with what I just said, right? Because what did I just say?
How many minutes are in a second?
How many minutes are in a second, right? So we know that that would be 160, right? So again, we have to pay attention, and that's what we get you on, right? On exams, on those multiple choice tests, we get you on how things are said. We don't get you on because you know what it is. You know what I'm saying, right? You know what I meant, right? Right? But it's not what I meant. It's what's written down there, right? Okay. So we always want to sit there and write stuff down, right? Because we want to make sure it makes sense. So we know that for every 1 minute, there is 60 seconds. You guys understand what I'm saying? Right? Yeah. Okay, right? Because I said how many minutes are in a second, right? And so we want to pay attention to what is being said and how things are written, right? Because that's going to be the key to solving the problem. So we know that there's 50 minutes, right? And we know for every 60 seconds, that's going to give us 1 minute. Okay, now, do you guys remember fractions? It's okay if you don't. We're going to work on it. We're going to work on it, okay? I know, because you guys all give me that look, but I'm going to teach you the simplest things about fractions today. You're going to remember. I promise you'll remember, right? So, if you have 4 over 4. Okay, what does that equal? 1. Okay, so if I have a number over itself, it's 1, right? What if I have x over x? No, it's 1. It still obey the rules. Anything over itself is going to be it's going to be 1, right? And so if I have x squared over x squared, x squared over x squared. That's going to equal 1, right? Okay, so all of those cases is going to equal 1, right? Now, what we're going to do is called dimensional analysis. Dimensional analysis is just basically using those multiplication, addition, and all those functions, adding to the units, right? So if I have a minute over a minute, what is that going to equal? 1. Okay, so anytime that you have a minute, and this line represents division, for a minute, it's going to allow the minutes to be canceled out. And so then we'd be left with just seconds. Okay, you guys see that? Okay, so then I get 50 times 60 seconds. So that would be 3,000. Okay. So units canceling out, it allows us to analyze the dimensions. So as we screw it up, excuse me. Let's say I did that mistake earlier where I switched those two, right? And you guys were telling me, oh, I have 60 minutes for 1 second. First off, we know that ain't true, right? The other thing that we know is that if we multiply that by 50 minutes, do the minutes cancel out? No, we end up with minutes squared. Right? So that clearly tells me I did something wrong, right? Well, first off, let's flip it so that it should be the right way, right? So that's one thing that we need to flip it, and then we also need to get those units, right? And so this helps us keep track of things, because otherwise we end up with a minute squared. Minute squared. Over seconds. Is that what we wanted? Okay, so we know that that's wrong. Okay, so that is dimensional analysis. How do you guys feel so far?
Good. I actually understood that.
Okay, let's see. Okay, so oldest horse racing track in the United States is the 8-furlong Pleasantation Fairground Racetrack in California. What is the length of the track in rods? 0.025 furlong is equal to 1 rod. It's given to you.
8. And so this,
It says.
so there's 8 furlongs.
So that's our given.
So we
Our
know
8
that,
furlongs.
we
Okay.
know that
Yeah.
0.025 furlongs is equal to 1.
Okay,
So it's
so
gonna be 8 times, or no,
we have 8 furlong.
yeah.
Eight furlongs in the equation, and it says 0.025 furlongs.
Okay, I like doing this little grid, right? And then the line represents division, right? It just like a normal line represents division. So we also know that 0.25 furlong equals 1 rod. So I want to get rid of what?
Furlong.
I want to get rid of the furlong. So I'm going to put that at the bottom. So 0.0 furlong. That equals 1 rod. So 8 divided by 0.025. So again, remember, the line represents division. 8 is on top, and we're going to divide it by this number. Okay, what's this here? 320?
Yeah.
Oops. Okay, so then your furlongs are going to cancel out, and we're left with just rods.
So 8 divided by 3.
Okay,
Times number 1
not too hard,
times 1.
pretty straightforward, simple.
8.
You guys remembering this from math? Long time ago, right? Okay, questions, concerns, cash? Everybody wants a little bit of cash, right? Okay. Okay. So what we just talked about, the furlong to a rod, that's called an equivalency, or it's called a conversion factor, right? So we use those to sit there and allow us to change from one unit to the next unit. And because we are in the US and we think US is right about everything, we have our own unit that nobody else in the world uses except us, right? So, because when we go to England, or if we go to France, or if we go to Poland, or anything like that, they don't use pounds, they use kilograms, right? As I was just telling you, dating apps, right? They'll say kilograms. You're like, girl, you know, they're like, you know, you see a picture and you're like, you said you're 100? No, right? Or you say you're 100, you know, or you're 50, and you're like, Lord, you need to get some meat on you, you know? So because we are in the US, we will often have to do a lot of conversions, right? And that's with temperature, because we like to use the Fahrenheit, right? Everybody else uses Celsius, or they use Kelvin. Science, you're going to use Kelvin. Because the length, we use feet, yards, right? They use kilometers, right? Time, pretty much everybody's consistent on time. So we're gonna have to play with conversion factors. If you guys look at your handout, I'm a strong believer. There's certain things that I want you guys to memorize. There's certain things that I believe Google is okay with, right? One of those things is your conversion factors. A lot of your conversion factors are, right? And so I give you guys the ability to sit there and use it, or I'll give them to you in the exam itself. Within the question, you'll have a conversion. Now, there are certain things that I do want you guys to know, right? So you need to be able to tell me if it's a small value or if it's a large value. Kind of thinking about things, right? And so we're going to talk about that a little bit, and I want you guys to remember that aspect of it, because that'll kind of help you figure out where things are supposed to be in the conversion factor, right? So if you guys take a look, there's nice little tables here that allow you to change, let's say, liters into pints, kilograms into ounces, into pounds, right? Meters into inches and feet, right? So I'm not expecting you guys to remember every conversion factor, but when we talk about the metric system, I want you to know the difference between a kilogram and a microgram, or a kilogram and a nanogram, okay? You guys understand? Okay, so if we write out the equivalency or conversion factor for the following, right? It says 1 day is equal to 24 hours. There are several ways that we can write this out, right? First off, we can say, as I said, 1 day, D representing day, equals 24 hours. We can also write it as 1 day over 24 hours. What is the other way I can write that? Or 24 hours over 1 day. So the beauty of conversion factors is that we can flip them around the way we want to flip around, or the way that we need them to flip around, right? And so often we will use that to sit there and go from 1 unit. So if I'm given 1 unit, I can change that to another unit. Okay. So if I tell you that my car averages 17 miles per gallon, right? So how many different ways can I write 17 miles per gallon? That per gallon, what does that mean? Per gallon. And for how many gallons? 1. So it's understood when it says per gallon, that means 1 gallon, right? So that's the same thing as saying 17 gallon or 17 miles. For 1 gallon. Right? Same thing. So if we see that per, we understand that that's going to be 1, right? Okay. Or I can say the same thing as 1 gallon. Miles. Or I could say 1 gallon. Okay, does that make sense?
Yes.
Okay. Okay. Okay, so how I say to work a problem, right? Now, there's 50 different ways of getting to the answer, right? I don't care how you get there, as long as you get there, but I always like to start off with the given, right? So we're often given a value, right? Given something, right? Earlier, we were given that time, and we know that we wanted to get to seconds, right? So I always know where I'm starting and know where I'm going, right? And then I kind of use my conversion factors to get me along the way. Now, if you think about it like this, you can solve pretty much any algebraic equation, anything, right? If you're given all the equivalencies, or if you remember all the equivalencies, right? Let me give you an example. Okay, here it says, calculate the number of weeks in 672 hours, right? So my starting is 672 hours. So I'm going to start my 672 hours. Okay, and what is it that I want? I want weeks. So I'm going to come over here and put weeks. At the end of the day, I want to end up with weeks. Okay, so what are some of the equivalencies I know about hours?
60 minutes is 1 hour.
First I heard there's 24 hours equals 1 day, right? Now, we could start with 64, we said 60 minutes equals 1 hour. Now I want to get to weeks. When I want to go back to minutes? Okay, so I probably wouldn't want to use that one, but that is one, right? There's 7 days in a week. Okay, so we have 7 days equals a week. Okay, so you can probably get away with just using these two, right? So we have hours on top. I want to get rid of hours. How am I going to get rid of hours? By putting in the bottom. So we have 24 hours. And we have 1 day on top. How many days are in a week?
7.
So I want to get rid of days. So I'm going to put days in the bottom. So my 7 days in the bottom. Okay, so my hours cancel out, my day cancel out, and then I'm left with just. Okay, so then I just multiply across, and then I divide it by the bottom. Okay. So what do you guys get? You get 4 weeks.
And 20%, whatever you get is gonna go over the 7 days. So figure, they said it's 20 days.
Okay,
But yeah.
questions? Pretty simple, right?
Yeah.
Now, this is so lovely, right? As long as you have the conversion, you can sit there and make this work, even if you don't know the equation or anything like that. You know what you're starting with, you know what you're ending with. If you have all the conversions, you can sit there and make it work, right? Okay.
So it'd be 672. So whatever you get from there would be over the 70.
Got it? Okay, so always remember that top, what you guys can do is multiply the top. And some people do it independently. They multiply everything that's on top. So that's 672 times 1 divided by 24 times 7, right? So they'll do them separately and then they'll divide the top by the bottom. You know, so both ways will give you the same answer. Okay, there's multiple ways to the answer. Okay, if you show me your work, makes it easy. Don't show me your work, I can't give you any points, right? Questions?
All the tests will be fill-in answers,
What do you mean by fill in the answers?
where you have to like take a picture of the word. Upload it.
Yes, yes, there will be short answers.
Conversions and stuff like
Short
that.
answers. I love conversion. I like to make it hard too. But I usually give you a practice question so that you'll know what you're getting yourself into. Okay? So, what is the distance expressed in miles when an automobile travels 3 hours at an average speed of 62 miles per hour? So what are we looking for?
And travel in the hours for 62 miles per hour.
So we're looking for what?
How much distance?
The distance. So unit should be what? If it's distance, it should be what? It should be miles, right? Miles is a distance, right? Okay, so we want miles. At the end of the day. Okay, what is our given? 3 hours. So we're starting out with 3 hours. Yes. Okay, good.
Yeah, I'm sure about that.
Okay. 3 hours. Okay, good. Did you guys submit your time cards? Sorry,
Yeah.
50 different things going on at once. Okay, so we have 3 hours. So how am I going to use that?
Maybe 1 hour to 60 minutes. I don't know.
1 hour. Okay, so should hour be on the top or on the bottom? Okay, so we should have 1 hour.
Bottom.
And then on top, we should have
60 minutes.
60 minutes, 62 miles, right? Because that's our conversion there, right?
Yeah.
Because we want miles. We don't want things in minutes. Okay, so then hours cancel out. Anybody colorblind? Again, if you are, let me know, because then I can make accommodations. Otherwise, I'll use all these weird colors and nothing will make sense to me. So then that is what? Okay, you guys understand? Okay, so again, we need to make sure that we're reading what the question is asking for, because DJ was just, throwing us a curve there. She kept saying minutes, minutes, minutes. She's obsessed with that 60 minutes, right? But we don't care about the minutes, right? Because we have hours, we have miles, right? We want miles, fuck the minutes, right? Okay, so we want to make sure that we're reading what the question's asking us, because otherwise we run down the wrong path. We waste time and money, right? Time is money, right? You guys understand that, right?
That's true.
Done, right? You want to get this done the first time, one and done. You want to make sure you understand. Right? Time is money. Okay, questions, concerns, Cash?
So my question, I do have a question. I was just a little confused because I didn't know that hours can go into miles. So we don't think about what, like, say if it was seconds to minutes, like, I don't know, maybe I'm overthinking.
Yeah,
Because
you are overthinking about it, right? So read the question for me.
it says, what distance expressed in miles will an automobile travel in 3 hours at an average speed of 62 miles per hour?
Okay, so in other words, they're giving us our conversion factor. That 62 miles per hour is acting as our conversion factor, right?
Okay.
Acting our equivalent. Okay, so they're giving us that in the problem. And so since they're giving it to us in the problem, we want to make sure that we utilize that, right? Otherwise, again, we start spinning our wheels for no reason, right? So we want to make sure that we pay attention to what's given to us. And sometimes, sometimes they give us extra information, right? And so then we have to parse out what they're trying to tell us, right? Don't worry, I'll give you guys an example of that because I like to do extra, right? Because a good person is able to sit there and parse out what's needed and what's not, right? Okay. Okay, so a little girl breaks her piggy bank. Inside, she finds 2,608 pennies. How many dollars does she have? Don't worry, I can find ways to make it.
No. Yeah.
So, what do we know about pennies? Okay, so we know that for every dollar, there's 100 pennies. So am I going to put the pennies on top or am I going to put the pennies on bottom? Okay, so I'm going to put my 100 pennies on bottom. And then $1 on top. So
26.08.
26.08.
$26.08.
Piece of cake so far?
Should start off with the pennies.
I should have started with the pennies.
Yeah.
Okay, I'll keep that in mind. I'll shuffle them around. Okay, so let's talk about the metric system. Okay, so like I said, we are in the US. We typically don't use the metric system, right? We are so against it. It's crazy, which I don't get because I like the metric system. Multiples of 10. Any of you guys play dominoes or anything like that?
Yeah.
Multiples of 10, right? Multiples of 5, multiples of 10, right? So it's real simple, right? 10, 100, 1,000. It's real simple, right? But we are so opposed to it, right? We've been trying to do this for the last, let's say, since I was in the 2nd grade. They were talking about changing our units to the metric system. They thought about it. But you notice we haven't done it yet, right? And we probably won't do it, especially now because things are kind of really crazy. But as scientists, because we need to be able to speak the international language, we have to learn 2 systems, right? We have to learn our system and we have to learn the metric system, right? We want to be bilingual in the sense, right? So it's going to be important for you guys to understand what the metric system is and how it's used, right? Particularly the scientists. And if you're a nurse, often you will be talking about centimeters and milliliters. You won't be talking about pints. Although because occasionally we'll talk about a pint of blood. We're going to take a pint of blood from you because people understand what a pint is, right? They drink beer, right? And so, but when you say you want to take a couple of cc's from them, they're looking at you like, what? So you're going to have to be able to tell them what that means. Oh, it's not that much. Ooh, we're gonna drain you dry, right? So you're gonna have to be able to distinguish that for them, okay? So it's important that you guys understand it so you can help your patients understand it. Okay, so let's talk about SI. SI units are basically the international standardized units that everybody likes to go by. So we have certain units that this is what typically people use in these cases, right? These are going to be our standards, okay? Now, the metric system is, again, it's based on tens, multiples of 10. So we have what we call our base unit, where everything kind of starts off at, and then we go. Let me give you an example here. Okay? So, for instance, we have the kilo. Kilo is typically 1,000 times our base unit. So if we have a kilogram, that's 1,000 times larger than a gram. If we have a kilometer, that is 1,000 times larger than a meter. Right? If we have a kilosecond, that's 1,000 times larger than a second. Okay, so whatever that base is, 1,000 times greater than that is going to be a kilo, right? So if I tell you guys you have a kilogram of something sugar, then how much sugar is that? It's going to be 1,000 grams of sugar, right? Okay. So if we use mil means 1,000 for us, right? In Spanish. You know speak Spanish, or am I fucking it up? If I am, let me know, because I will mess it
Are you
up.
trying to say me?
Mil.
Me.
Mil. Isn't that what I said? Mil.
Me.
Mil.
Me.
Mil.
Yeah.
I guess I'm messing it up. How is it different than how you say it? Mil.
Me.
Me.
Me. Me.
Mil, right? Means 1,000, right? Does it not mean 1,000? Mil.
Yeah.
Mil. Okay. I just don't say it right. Okay, I'll work on it. Okay. Meal means 1,000. In this case, it's 1,000 times smaller than a gram.